All right, let's talk about linear algebra. If you've ever felt like it's this impossibly complex subject, you are in the right place. Today, we're going to crack open a really tough-looking problem and show you the elegant, super powerful secret hiding inside. It's a shortcut that is seriously clever.
So let's kick things off with a challenge for you. Imagine you've got this 3x3 matrix, we'll just call it A. And your mission, should you choose to accept it, is to calculate a to the power of 100. Yeah, that means multiplying a by itself 99 times.
I mean, can you imagine doing that by hand? It would take forever. It sounds like an absolute computational nightmare, right? But what if I told you there's a brilliant shortcut that lets you skip all of that repetitive, painful work?
To unlock this shortcut, we first need to find a few key ingredients, and they're hidden right inside the matrix itself. You can think of them as the matrix's magic numbers, its secret code. And these numbers reveal its most fundamental properties, the same properties that help us understand everything from how Google ranks websites to how to build a stable bridge. These numbers are called eigenvalues. You know, in German, the word eigen means own or characteristic. So these are literally the characteristic values of a matrix. They're the secret scaling factors that tell us exactly how that matrix stretches or shrinks things.
Okay, so how do we actually find them? Well, it's a pretty straightforward three-step process. You always start by setting up what's called the characteristic equation, the determinant of a minus lambda I equals 0. This is always step one on our treasure hunt for the eigenvalues.
Now, for the example matrix we're working with here, once you set up that determinant and solve it, this is the polynomial equation you get. This is kind of the heart of the puzzle we need to solve to find our magic numbers.
Solving a cubic equation like this can look pretty scary, I know, but we've got tools for it. As the source shows, you can use something like the rational root theorem to get your first clue, to find the first root. From there, a little synthetic division knocks it down to a simple quadratic equation, which is super easy to factor. And that reveals all three of our hidden eigenvalues.
And there we have it. We found them. Our three magic numbers are 8, 2, and yep, another 2. It's totally normal, by the way, for these numbers to repeat. That's a common and pretty important thing that can happen.
Okay, we're halfway there. So we've got our magic numbers. Now let's find the next ingredient. It turns out each of those eigenvalues has its own partner, a kind of magic vector that it's paired with.
And these are called eigenvectors. Now, what makes them so special is this. When our matrix A multiplies them, it doesn't knock them off course. Their direction doesn't change one bit. All that happens is they get stretched or shrunk, and the factor they get stretched by, you guessed it, it's their eigenvalue.
And the process for finding these vectors is also really methodical. For each eigenvalue we just found, we plug it back into this formula, a minus lambda I times x equals 0, and then we just solve for the vector x.
So you do the math for our eigenvalue of 8, then for the eigenvalue of 2, and then for the other 2, and what you end up with are these three corresponding eigenvectors. We've got the whole set now, our magic numbers and their magic vectors.
All right, this is the moment we've been building up to. We have the eigenvalues, we have the eigenvectors, we have all the pieces we need to finally put together our amazing shortcut for calculating a to the power of 100.
And the reason this all works, the mathematical principle that makes this whole shortcut possible, is called the diagonalization theorem. It basically just says that if you can find enough of these independent eigenvectors for your matrix, in our case 3 for our 3x3 matrix, then you're good to go. You can use this method.
And here it is, the shortcut itself, all wrapped up in one beautiful formula. It tells us we can actually rewrite our original complicated matrix A as the product of three much simpler matrices, P, D, and the inverse of P.
So let's look at the pieces. D is the real hero here. It's called a diagonal matrix, which is just a fancy way of saying it's super simple to work with. It's literally just our eigenvalues, 8, 2, and 2, sitting on the main diagonal, with zeros everywhere else. Easy, right?
And what about P? Well, that's just as easy. You just take the three eigenvectors we found, and you stand them up side by side to make the columns of a new matrix. That's it. And P inverse? That's just its matrix inverse, which is a standard thing to calculate.
So, let's bring it all home. We've broken down our matrix A into P, D, and P inverse. But how in the world does this help us with our original problem, calculating a to the power of 100?
This is where the magic really kicks in. When you raise a to some power, let's call it k, it turns out that because of the way p and p inverse cancel each other out in the middle,
You only have to raise that super simple D matrix to that power. All the hard work gets shifted to the easiest part of the problem.
I mean, just look at the difference here. Calculating a to the 100th power is like trying to push a giant boulder up a hill. But calculating d to the 100th? That's a piece of cake. You just raise each individual number on the diagonal to that power. A ridiculously hard problem just became trivial.
So, to get our final answer for a to the 100, we just assemble the pieces. We take our super easy to calculate d to the 100, and we simply multiply by p on the left and p inverse on the right. And boom, that's it. We have completely sidestepped multiplying a by itself 99 times. We've solved a massive problem with a truly elegant shortcut. That is the power of diagonalization.
And this just leaves you with this really cool thought. This whole method, finding a system's core eigenvalues and eigenvectors, it's not just some abstract math trick. It is the engine behind Google's PageRank algorithm. It's used to analyze vibrations in bridges to keep them safe. It's even used to describe energy states in quantum mechanics. So the question is, what other complex systems out there could be simplified if we just knew how to find their magic numbers?